So our next sample problem here expands on the concept of having Lewis structures that have multiple bonds and asks the question, are there different ways that you can draw this structure with a position of where the double bond is that would allow you to kind of distribute some charge density throughout your molecule? So again, and another thing that's kind of brought in with drawing a Lewis structure for this molecule is we haven't yet drawn a Lewis structure for something that is a polyatomic ion. So we've got the nitrate ion here. So here's how we draw the Lewis structure for that. 5 electrons for nitrogen plus 18 electrons from the 3 oxygen atoms, each coming with 6 electrons. And because we have a polyatomic ion with a -1 charge, we need to add 1 more electron. That gives us a total of 24 electrons that we have to glue these atoms together. If we space them, and we use up 6 electrons for that spacing, we're going to be left with 18. 2, 4, 6, 8, 10, 12, 14, 16, and I've already done enough of these problems that I'm going to hedge my bets that I'm going to put those as a shared pair because that gives my nitrogen a complete octet. Let's go through and check formal charges here. Each of these oxygens is going to have a formal charge of -1. Again, if seeing how that's a formal charge of -1 is confusing, go back and review some of the earlier sample problems where we went through some more detail for calculating formal charge. Formal charge on this nitrogen is going to be +1. One of the important things to remember with formal charges is that the formal charges of your Lewis structure must all add up. The formal charges on all of your atoms must add up to the overall charge on your species. And in this case, since our overall charge has a -1, adding up these formal charges to -1 is consistent with that. So, valid Lewis structure. But one of the things that we can do is, how come this oxygen got to be the one that didn't have to have a formal charge? Well, we can draw a resonance structure. And when we draw a resonance structure, we use a special arrow to indicate we're showing resonance structures, which is a single line with 2 arrowheads. We don't want to draw something like this, because that implies that these 2 species are interconverting with one another. And as we talked about in class, and as I'll highlight here, these structures don't really exist. The reality is that it's a mixture or a hybrid of all of these structures is the reality of the Lewis structure for this species. But let's go ahead and draw another Lewis structure, which has the oxygen on the left, for example, being the one that has the double bond. The other 2 oxygen atoms then must each have a -1 formal charge, and that doesn't change the formal charge that we have on our nitrogen atom. We can go ahead and draw one more Lewis structure, which again is going to put the nitrogen-oxygen double bond on the lowermost oxygen atom. One of the things that you'll note here is sometimes formal charges are drawn with a +1 or a plus whatever the charge is. Sometimes it's just drawn as a plus or a minus symbol if it's just plus or -1. And again, usually you circle those to make sure that they don't get lost in the clutter of what you're drawing here. So we can draw 3 possible Lewis structures, and as we'll see when we get to a problem in just a moment, we can evaluate which Lewis structure is going to be the best. And in this case, there's actually not a difference. The symmetry of this molecule is such that there's no preference for any one of these oxygen atoms to be the ones that own the formal charge or that are participating in the double bond. One of the things that's not explicitly written in this problem, but I'd like to kind of add to it, is let's draw the resonance hybrid. Because the hybrid is really the reality of what this molecule looks like. And so you can imagine the hybrid really being a summation of all of these, where every atom is connected by single bonds, but any place that you had kind of a double bond, we're going to draw as a dotted line. So kind of we're taking and spreading electron density between all of these atoms. It's a little bit hard to draw with this molecule because we kind of have to cross over where single bonds are. But this just kind of is a way to show that that electron density from this double bond is spread over all 3 oxygen atoms. Another thing that this problem does ask us to do is calculate bond order. And bond order is a little bit weird to think about. And I'm going to say we're going to calculate bond order by taking a value that I'm going to define as A and dividing by a value that I'll define as B. And the value that I'm going to define as A is the number of shared electron pairs. So really, how many electron pairs are being shared by molecules that are part of kind of this resonance hybrid? So again, there's 4 atoms that are kind of participating in what's going on here. And so there's 4 electron pairs that are being shared throughout those atoms. So again, 4 electron pairs is the number that we want to put in here for what I'm defining as our A value. Our B value is the number of bonded atoms. So bonded atom pairs. And this is a little bit weird to think about, but this number is going to be 3, and see if this makes sense. If I look at what's going on here, I've got 1 bonded atom pair there, another one there, and then another one there. So it's kind of weird because that nitrogen atom is actually part of 3 different bonded atom pairs. So even though there's only 4 atoms there, there's 3 bonded atom pairs. And that's because we have a central atom here bonded to 3 other atoms. So when we take and we divide this, we get 1 1/3. And so the bond order is really 1 1/3. And with this structure, it can kind of make sense that 1/3 of the time, this is going to be a double bond. The other 2/3 of the time, it's a single bond. So the bond between nitrogen and oxygen is neither single, which would have a bond order of 1, nor double, which would have a bond order of 2. It's somewhere in between, and we can kind of logically make sense of the reason that it's 1 1/3, because 1 out of 3 times this molecule is going to have this nitrogen double bonded to this oxygen. The other 2/3 of the time, it's going to be a single bond. And I'm saying that for us to conceptually understand this bond order. It's important that you understand that these are not individual molecules that exist and that we just basically kind of switch back and forth between. The reality is that our resonance structures represent localized or electrons in fixed positions, whereas the hybrid is really the reality of what this molecule looks like.